Mount Rainier is considered to be an active volcano seismically, but scientists say right now people are misinterpreting data and what they're seeing is not a sign of a blast.
Mount Rainier. Mount Rainier.
Mount Rainier.
Mount Rainier.
A rare alert rippled across the Pacific Northwest. Major highways near active volcanoes were closed. Airspace filled with monitoring aircraft. Evacuation notices reached towns scattered along the Cascade Range. The U.S. Geological Survey had ordered unprecedented restrictions across the Cascade Volcano Corridor from Mount Baker to Mount Shasta. In the early hours of spring, a rare alert rippled across the Pacific Northwest. Major highways near active volcanoes were closed. Airspace filled with monitoring aircraft. Evacuation notices reached towns scattered along the Cascade Range. The U.S. Geological Survey had ordered unprecedented restrictions across the Cascade Volcano Corridor, stretching from Mount Baker near the Canadian border to Mount Shasta in Northern California. Officials stressed this was not a response to a single eruption threat. Instead, the move followed a convergence of unusual signals across multiple volcanic systems. Elevated seismic activity, changes in ground deformation, and shifts in subsurface behavior detected beneath several Cascade peaks. While no super-eruption was declared imminent, the scale and coordination of the response signaled heightened concern. The Cascades are not one volcano but a connected chain, dozens of magma systems linked by deep tectonic forces. When activity rises across the corridor at once, scientists pay close attention. The question now facing the region is not whether one volcano will erupt, but whether the entire system is entering a new, more unstable phase. Chapter 1. Shocking shutdown. Secrecy or survival? What do officials know that the public doesn't? And why did they move so quickly, so decisively, to shut down the entire Cascade Volcano Corridor? The order came with the force of a landslide, catching even seasoned geologists off guard. One day the corridor buzzed with hikers, researchers, curiosity seekers. The next, the access points were blocked, the parks deserted, the air of adventure replaced by the dull anxiety of uncertainty. Reports from the United States Geological Survey insisted there was no sign of an imminent super-eruption. They called out fake news and clickbait, determined to tamp down on panic. But the timing was impossible to ignore. Why pull the plug on such a vast region, a line of fire stretching for hundreds of miles, if there was truly nothing brewing beneath? In situations like these, science aims to measure risk, not remove it entirely. The fact is, the shutdown wasn't about a single cataclysm. It reflected something far more complex, a growing web of warnings, shifts in magma, subtle quakes, mysterious gas leaks, each too small to ignite its own alarm, but layered together, building toward an inescapable verdict. The corridor was closed not out of certainty, but out of prudent doubt. When the stakes are measured in cities, coastlines, and lives, even a shadow of possibility becomes too heavy to ignore. Is this secrecy or survival? And what clues are hidden in the tapestry of tremors that ripple through the Cascades, waiting for those who know how to read them? Chapter 2. Satellite surveillance. Eyes in the sky. Are satellites seeing dangers scientists can't admit on the ground? High above the Cascade Arc, a silent fleet of satellites kept vigil. From low Earth orbit, their sensors mapped the shifting skin of the mountain range with more precision than any ground observer. These watchers in orbit, outfitted with radar, thermal cameras, and other advanced detectors, could see what even the most intrepid geologist on foot could not: the subtle rising of entire ridges, the heat of magma surging closer to the surface, the spidery patterns of faults deep within the crust. This unblinking surveillance paints a haunting picture. Over the last 18 months, certain peaks in the Cascades have begun to show ground deformation, sometimes just millimeters, sometimes centimeters a month, a sign that molten rock is on the move, pushing upward. These are not the violent, explosive bulges seen before famous eruptions like Mount St. Helens in 1980. No, these are quieter, slower, more insidious. Growth that, at first glance, might be dismissed as the benign settling of a living planet. But pattern-hungry algorithms, running around the clock, see things differently. They connect the dots, finding a chorus of rising summits and subtle ground deformation, not as isolated incidents, but as threads of the same simmering storyline. Is it just the breathing of these ancient mountains, or the first warnings of a corridor waking up all at once? Chapter 3. Seismic chatter, the awakening. Are the Cascades telling their secrets through earthquakes? Beneath the velvet silence of snow-laden forests, a new kind of noise has begun to build. A trembling, a clicking, a chorus of seismic chatter. Instruments buried along the flanks of these volcanoes now record persistent earthquake swarms. Unlike the dramatic jolts of major faults, these tremors are quieter, occurring in clusters, often too small for anyone on the surface to notice. But when geologists map these swarms, a revealing picture emerges. The quakes are not confined to the infamous hotspots, rain-shadowed Mount Rainier, brooding Mount Hood, but ripple outward into valleys thought to be stable. Each cluster marks a slip in the Earth's crust, the slow, stubborn migration of molten rock, building pressure as it seeks a path to freedom. The pattern echoes recent history. In 2025, an earthquake swarm at Mount Rainier was not the beginning of an eruption, but served as a powerful reminder. The Cascade volcanoes remain restless. A single event may pass quietly, but the chorus, the rising tempo, is impossible to ignore. Do these hidden conversations portend a threat no one wants to speak aloud? Or is restlessness simply part of a vast volcanic system's nature? Chapter 4. Underwater volcanoes, a new front. Could a Pacific volcano influence the fate of the Cascades? Far to the northwest, deep in the Pacific's shadowed abyss, a powerful underwater volcano recently showed signs of increased activity. Seafloor monitors recorded its awakening. Swelling magma, rising terraces, a silent beacon pulsing through stone and salt water. News of this distant eruption barely made a ripple on land, and yet, beneath the surface, its impact could be worth monitoring. There is evidence of connections, a network of faults capable of transmitting tremors across regions. Scientists ask, what happens when an underwater quake or eruption in Alaska's frozen corner and the seafloor triggers a chain reaction down the volcanic corridor of the West? Recent events suggest the Cascades don't exist in isolation. Tremors and surges from the seafloor can subtly redistribute stress under North America's great mountain ranges. Is the true threat to the Cascades actually born in the pulse of the Pacific itself? And when magma stirs beneath distant waves, does the entire spine of fire in North America respond in kind? Chapter 5. Faults beneath, the invisible threat. Is a hidden fault line beneath the U.S. about to change everything? Beneath the feet of millions, cracks wait, some so ancient they predate the Cascade volcanoes themselves. Occasionally, research points to large, concealed faults showing new signals of activity. When faults once considered dormant awaken, they introduce uncertainties into forecasts. Most earthquakes in the Cascades stem from volcanic activity, magma moving, gases expanding, crust shifting. But an awakening fault that's not part of the regular map introduces chaos. If such a fault slips, the consequences could ripple upward, shaking the very foundations of these volcanoes, and perhaps leading to unexpected events beyond the capacity of existing monitoring networks to predict. Could the next big one in the Cascades come not from inside the volcanoes, but from the very bedrock beneath them? An old wound reopening, shaping events in ways yet to be fully understood. Chapter 6. Alaska's Mount Spur, the chilling parallel. Can the secrets of Mount Spur warn us before time runs out? All eyes turned north as reports came in from Alaska's Mount Spur, a peak as remote as it is unpredictable. Here activity began to mount. Earthquake swarms, creaking glaciers, and the measured swelling of the mountain's flank. It wasn't just the seismic activity. It was the speed of the changes and the familiarity of their patterns with those seen farther south. Why does what happens in Alaska matter for the Cascades? The answer is striking. Tectonic systems don't stop at state lines. Stress changes in the north can translate into minor shifts in the south, like a slow-motion chain reaction. When Mount Spur stirs, it is a reminder. Even volcanoes separated by hundreds of miles are sometimes connected, if only through the stress and tension that travels through Earth's crust. Could a shift in Alaska send a warning signal to the Cascades? And is the corridor shutdown meant to guard against such a chain of events? Chapter 7. Patterns of swelling. Mountains on the move. Is swelling ground a code to be cracked, or a countdown we can't decipher? Mountains are not as static as they seem. Over the last year, a handful of Cascade peaks have shown a consistent, nearly invisible phenomenon: uplift. Week after week, satellites logged small but measurable swelling, sometimes imperceptible, sometimes evident enough to raise professional eyebrows. This kind of motion is the hallmark of pressurized magma, moving closer to the surface. But the true concern lies in the patterns emerging across the region. It's not just one mountain. There are signals from Mount Rainier's southeast flank, an uptilt near Crater Lake, a change in Mount St. Helens western rim. Each data point on its own might be dismissed. Taken together, they form a map, a coded warning from the planet. Are these swells harmless adjustments? Or is the corridor preparing for an event larger than any in living memory? Scientists point out that periods of inflation do not always lead to eruptions, but must be watched with vigilance. Chapter 8. The super-eruption myth. Fact versus fiction. Why are warnings about super-eruptions called fake news? And what's the real story scientists won't say? Every headline and rumor speaks of a super-eruption, an event so immense it would blanket continents in ash and end modern society as we know it. But the United States Geological Survey stands firm. There is no evidence of any impending super-eruption in the Cascades, and it is unlikely one will occur in the foreseeable future. Why the divide between fact and fear? Science deals in probabilities, not absolutes. While the idea of a catastrophic eruption makes for compelling stories and viral content, the data so far reveals a different kind of risk, a corridor not primed for a single apocalypse, but for a complex web of smaller, interconnected dangers. Cascading failures, triggered by faults, fed by magma, amplified by even minor eruptions. The danger is real, but it isn't the one people expect. Is our obsession with the spectacular hiding the truer, subtler risks, those that creep, not crash, into our lives? Chapter 9. Earthquake swarms, the murmuring below. Are earthquake swarms Mother Nature's code red, or just noise in the dark? The past few seasons have seen the rise of the swarm, a new rhythm beneath the old peaks. Hundreds of tiny earthquakes jostle and ricochet beneath the still forests, too small to shake bridges but big enough to catch the trained attention of seismologists. What do these swarms mean? In volcanic corridors, they often signal magma moving underground, fracturing rock as it goes. Even if none breach the surface, the pressure builds, and the risk of a trigger event, an eruption, a landslide, a sudden gas outburst, grows. Could these clusters be the warning shots Mother Nature gives before a corridor-wide event? Or are they simply the background music of a restless planet, a reminder of the constant motion beneath our feet? Chapter 10. Triple junctions, where chaos begins. Can the intersection of fault lines birth a disaster no model can predict? Inside the tangled geometry of the Earth's crust, there are places where three tectonic boundaries meet, triple junctions. These are zones of instability and stress. The Cascade Corridor is influenced by such intersections, where spreading ridges and transform faults converge and scramble the rules of seismic behavior. Each triple junction acts as a relief valve, a place where stress can sometimes escape. But these are also potential birthplaces for microplates, fragments breaking free and changing the landscape of geological risk with every tremor. Are these junctions keeping the corridor safe by letting off steam? Or could one misstep here trigger a domino effect, shifting stability across regions? Chapter 11. Microplates, a corridor in pieces. Are splintering microplates the hidden prelude to a corridor collapse? The image of tectonic plates as monolithic, unchanging slabs is an illusion. Across the Cascade Corridor, microplates are forming, tiny shards breaking loose from the larger Pacific plate. Each one subtly redefines the underground terrain. Researchers track these microplates with interest, knowing their movements can create new faults and amplify existing ones. As they slip and slide, pressure redistributes in ways difficult to anticipate, sometimes leading to surprise earthquakes or shifts. Could this fracturing be a warning that the Cascade Corridor is entering a period of subtle, complicated change? The ground beneath our feet, constantly rewritten by these splinters, reminds us that stability is only ever temporary. Chapter 12. Ring of Fire, the pressure mounts. Is the world's most dangerous volcanic zone about to rewrite the fate of the Cascades? The Cascades are only a chapter in a much larger story, the Ring of Fire, a chain of volcanoes and fault lines circling the Pacific. This ring produces 3/4 of all active volcanoes on Earth, and nearly all of the world's biggest earthquakes. Its most violent eruptions and deadliest quakes have shaped human history. What happens when pressure in one part of the ring migrates, as it often does, when stress relieved in Japan or South America quietly builds up in the Pacific Northwest? Each quake, each eruption, ripples around the ring, a message in seismic code. The closure of the Cascade Volcano Corridor may hint at deeper worries, that the region isn't just reacting to its own stresses, but to ongoing shifting tension around the entire Pacific Rim. Will the next surge in the Ring of Fire force the Cascade Corridor to become the next headline, a disaster zone instead of another warning? Chapter 13. Historic Parallels. Lessons from Lost Giants. Are the ghosts of ancient plates warning us of a coming collapse? Long before the United States drew any lines on a map, a brooding giant sprawled beneath the Pacific, the Farallon Plate. For millions of years it dominated the region, only to break apart under relentless subduction. Its remnants now persist as smaller plates like the Nazca, Cocos, and Juan de Fuca plates. The latter drives the notorious Cascadia subduction zone, infamous for megaquakes and tsunamis. History offers a lesson: no plate is forever. The instability that broke the Farallon is now seen in how present-day plates interact. The Cascades, long considered stable, now show subtle changes not unlike those observed before the Farallon's final collapse. Could we be witnessing the early stages of a similar process, one that remakes coastlines, cities, and the very makeup of North America? Or are these just echoes from a restless past, urging us to watch, not to panic? Chapter 14. Cascadia Subduction Zone, the ticking bomb. How close is the Northwest to another megathrust nightmare? Of all the dangers smoldering beneath the Cascade Corridor, none loom larger than the Cascadia Subduction Zone, a seam off the Pacific coast where the Juan de Fuca Plate dives beneath North America. Every few centuries, this fault delivers a mega-earthquake, with the last in 1700 unleashing a tsunami so great it was recorded in Japan. What's the risk now? Every time pressure redistributes across the corridor, by quake, by swelling, by fault slip, the subduction zone builds toward its next big event. Scientists closely monitor the signs, aware that the next rupture could bring not just ground-shaking chaos, but tsunamis, flooding, and long-term disruption for millions. Is the shutdown of the volcano corridor a cautious step to prepare for the unknown? Or simply a way to buy time, a chance to refine early warning systems before nature decides to act? Chapter 15. A corridor on the edge. Will this unprecedented shutdown prove a masterstroke of prevention, or an admission that nature is always one step ahead? As the months go by and the public grows restless, the Cascade Volcano Corridor remains silent, its trails deserted, its warnings multiplying. Each day brings new data: a pulse of gas, a shallow quake, a mountain's subtle rise or fall. Networks of satellites, scientists, and emergency managers, every tool in mind, wait for the moment when science crosses from caution to crisis. There are no easy answers. Every new discovery in the earth sciences frames this region as a place in conversation with disaster, a corridor held together by vigilance and hope that early warnings might come before the final trigger. The shutdown could buy precious time. Or maybe in the end it's the mountains themselves, ancient, indifferent, and alive in ways we barely understand, that will decide our fate. One thing remains certain: the Cascade Volcano Corridor will not sleep forever. Its future shape, broken or whole, peaceful or raging, may already be writing itself far beneath our feet. The only question that counts is whether we'll heed its warnings in time to prepare. If you want more deep dives into the Earth's mysteries, fault lines, and volcanoes, be sure to subscribe. The next chapter may already be unfolding beneath us.